about how to find the domain and range of quadratic functions. A quadratic function is a function that has the general form f of x equals ax squared plus bx plus c. Now, for example, 2x squared minus 5x plus 4, in which case our a is equal to 2, our b is equal to -5, and our c is equal to 4. So this is the general form of the quadratic function. And how do you find the domain of a quadratic function? Now first, let's talk about why the quadratic function is a function but not a relation. Now every relation that is a function, we all know that it must pass what is known as the vertical test. That is, if you drew a vertical line through the curve at any point, any one point, then it must cut the curve at only one point. And that is to say that any x value here must have only one corresponding value. This is different from a curve like that. Let's look at this curve. If I were to draw a vertical line through this curve, you will see that it will cut it at two different points. And so one x value here is going to get two different y values there. And so this is not a function, this is a relation. And so the first thing I wanted to establish is that the quadratic relation or expression is a function. And how do you get the domain of a quadratic function? Now, if you were to draw the graph of a quadratic function, there are going to be only two forms. One form is going to look that way, where we say that it has a turning point that is minimum, lowest point on the curve. This point is known as the vertex, and it is written in terms of an x-coordinate and a y-coordinate. Let's call the x-coordinate h and the y-coordinate k. This is going to be the lowest point on the curve. It means that below that point, below this point, we don't know the curve. So the curve is not defined here, below this point, below the lowest point. And that is when we are looking at the y-coordinate. But along the x-axis, the curve is always going to be defined. It doesn't matter where it is. The curve can appear here where it is not cutting the x-axis, in which case we say that the curve does not have any real roots. But if we were to extend this curve, you will see that it will go into the negative x region here. If the curve happens to be somewhere there and we extend it, it will enter into the positive x region somewhere here. If the curve were to be somewhere there and we extend this, it will enter into the negative region. So wherever the curve lies, it has both x, negative x, and positive x values. Now, this is not the only shape that we can get. We get this shape only when a is greater than 0, when a is positive. And so, for example, something like 2x squared plus 6x minus 9, because this 2 is positive, the curve is going to be, we say, concave upwards, this way with a minimum turning point. But if a is negative, that is when a is less than 0, then the curve that we are going to get is going to be convex downwards with the highest point. So when a is less than 0, for example, minus x squared plus 6x plus 9, then the graph of this curve is going to look something like that. And it is always going to get a maximum point, a maximum vectors, a vectors which is maximum h and k. Alright. But then the curve is going to lie in both the x, the positive x, and then the negative x regions. And so generally we say that for a quadratic function, the domain is always, so the domain of a quadratic function is always x is such that x belongs to the set of real numbers. And in this form, we say that we are writing the domain in the set builder notation form. Or we can say that the domain is from negative infinity to positive infinity. And this is the interval notation form. So any of these two will work. So whatever quadratic function that you are given, the domain is always and always the set of all real numbers. For example, let's assume you are asked to determine the domain of the following. Number 1, f of x equals x squared. Number 2, f of x equals minus x squared plus 1. Number 3, f of x is equal to negative 2x squared plus 6x minus 7. It doesn't matter, the domain of this is from negative infinity to infinity. The domain of that is from negative infinity to infinity. And this one also has a domain of negative infinity to infinity. Now let's find the range of a quadratic function with a minimum turning point. Now for the function in the form ax squared plus bx plus c, if a is greater than 0, I stated that the graph is going to look this way with a minimum turning point. At this point we call it the vectors of the curve, and the graph will never go below the vectors. If the x coordinate of the vectors is h and the y coordinate is k, then at k here we will never get the graph below it. So at this point of the graph we don't know what is there, so that point is not defined. And so what we say is that the range of a quadratic function with a minimum turning point is always going to be y is such that y is greater or equal to k. And so what we need to do, our duty, is to be able to find this k. Once we get a k, we can get a range. And what this means is that this y is always be above the k, from k upwards. From k upwards. Because below k, we don't know where the graph lies. Now, given the function f of x equals ax squared plus bx plus c, where we are assuming that a is greater than 0, the x component of the vectors h is given as x equals minus p over 2a. Now once you get this value for x, you can just come and slot it in this function and you'll get a value for k. This is one of the ways by which you can find the range. And so for example, let's assume that I ask you to find the range for f of x is equal to x squared minus 2x plus 1. Now, f of x equals x squared minus 2x plus 1 when compared with ax squared plus bx plus c. We said that the x component of the vectors is minus b over 2a. And so when we put b to be equal to minus 2, as you can see here, a is equal to 1 here into this expression, then we get x to be equal to minus 2 over 2 times 1, which is equal to 1. And so our h is equal to 1. Remember, our vectors was given as h and k. And so our h is equal to 1. Now this one stands for y component of the vectors, and that is the x. And in every ordered pair equation, once you get x, when you put it back into the equation, you can get your y. And so what we do is that we put h equals 1 back into the function. And so f1 becomes x squared minus 2 times 1 plus 1, which is 0. Now what it means is that our vectors is 1 and 0. Now let's try and sketch this equation. Now, the vector is the point that the curve is turning itself. And we know the shape of this curve to be this way because a here is greater than 0, it is 1. And it's going to turn itself at 1 and 0. It means that when x is 1, y is 0. It is on the x-axis. Now how do I get, we are not doing curve sketching, but I want to talk a little bit about this. Where do I get this 1? You know that on the y-axis, x is always equal to 0. So all you do is that when you put x to be equal to 0 here, everything here will go to 0. And so the graph will cut the y-axis at 1. Now from here, you can go ahead and then write your range. So what is our range? Our range will not go below the minimum point on the y-axis. And the minimum point is 0. So we are going to say that our range is y is such that y is greater or equal to 0. And that's it. Another way by which we can find our k is to use this formula, that k is always equal to minus b squared plus 4ac all over 2a. And our a is equal to 1 here. Our b is equal to minus 2 there. And then the c is equal to 1 here. And so in this example, we calculate k straight away. We don't find x or h and put it back into the equation before we get k. We just use this to get our k. And so we just teach that our k is equal to minus 2 squared plus 4 times a is 1, c is 1, all over 2 times 1. Now this gives us minus 4 plus 4 over 2, which is 0 over 2, which is 0. And so our k is again 0. And we say that our range is equal to y is such that y is greater or equal to 0. And that's it. Now, a third method that I want us to look at is the method of completing squares. We can complete the squares and then use that to find the range of a quadratic function. And how do we do that? All we are going to do is that we are going to find half of the coefficient of x, minus 2 over 2. Half of this is you divide minus 2 by 2, and this is equal to minus 1. Then we are going to square minus 1 and add it and subtract it again. And so we are going to write this expression as x squared minus 2x plus minus 1 squared, that is the half squared. We are adding it, and then I want to subtract it again. I haven't done anything to it. Minus 1 squared, and then I have plus 1 here. Then I'm going to take this and that because it gives us the whole squared expression. So I have x minus 1 squared. Then here, remember we have minus 1 squared is 1 plus 1. Now this gives us x minus 1 squared plus 0. That is f of x is equal to that. Now whenever you write a quadratic equation in the form x in the form a x minus h squared plus k, then whatever number you get standing here is our k. And you see that our k is still 0. And so from there, knowing that this is a minimum curve, knowing that this is positive, and knowing that the curve is going to turn itself at k equals 0 on the y-axis, right? We just see that our range is equal to y is such that y is greater or equal to 0. Now, let's take this question using the method of completing squares. The question says that you find the range of 2x squared plus 3x plus 8 by the method of completing squares. Now, by the method of completing squares, all we have to do is to write the quadratic expression for the quadratic function in the form y equals ax minus h all squared plus k. Now what our target is k, and because we know that this is positive, we know the graph is going to have a minimum value. So let's go ahead and do this. Now we have f of x is equal to 2x squared plus 3x plus 8. Now what we do is that we factorize 2 out and bring 2 out. We want to make the coefficient of x squared unity. Then you divide here by 2, you get x squared. You divide the 3x by 2, you get 3 over 2x. Then you divide the 8 by 2, you will get 4. Now this becomes 2. And the next time what we are going to do is that we are going to find half of 3 over 2. Half of the number attached to x, the coefficient of x. And half of 3 over 2 is 3 over 2 divided by 2. It gives us 3 over 4. So 3 over 2x plus this 3 over 4. Then we square it. Then let's subtract it again. We haven't done anything to this expression at all. We added it and then we are subtracting it. Remember there is a 4 at the back. Then we are going to take our squared quantities. When you expand this, you will get this whole expression. And so you don't take the 3 over 2x in addition. So you have x plus 3 over 4 squared. Remember there is a 2 outside. And then plus 4. Sorry. And then we have minus 9 over 16 plus 4. Let's write this as 4 over 1. Now this gives us 2 x plus 3 over 4 squared minus 9 over 16. I want to write this as 4 times 16 over 1 times 16. And so this gives us 2x plus 3 over 4 squared minus 9 plus 64. That's 4 plus 16 is 64. I don't know why I wrote 14 here. 64 all over 16. Right? And this gives us 2 outside. X plus 3 over 4 all squared minus 9 plus 64 is going to give us 55 over 16. Now when we expand these two, we are going to get 2x plus 3 over 4 squared. And then when we expand 2 times 55 over 16, 2 goes into 16 8 times, so we get plus 55 over 8. And so when we compare this with the general form of the vertex, we see that our h is equal to minus 3 over 4 and our k is 55 over 8. For the range, what we are interested in is the k. And we know that our curve is going to have a minimum point because the number attached to the x squared, the coefficient of x squared, was positive. So our k on the y-axis is going to 55 over 8, which means that this graph can never go below 55 over 8. And so our range, we can say, is from 55 over 8 to infinity, or we write this as y is such that y is greater or equal to 55 over 8. And we are done. Now let's find the domain and range of the quadratic function here. This one, because the coefficient of x squared is negative, because this is negative, we are going to get a maximum graph, something that is going to look like that. And whatever value we get here on the y-axis, k, the graph above it, we don't know it. So that part of the graph curve is not defined. And so our y is going to be such that y is always going to be less or equal to the k. This is the part of the graph that is defined. This is what we can work with. And so let's use our method of completing squares to find the range of this function. And so let's start by making the coefficient of x squared unity. And so we factorize out minus 2. Now we divide minus 2x squared by minus 2, we get x squared. And then we divide minus 3x by minus 2, we get 3 over 2x. And then when we divide 2 by minus 2, we get minus 1. Now let's find half the square of the coefficient of s. So plus 3 over 2x. Half of 3 over 2 is 3 over 4. So let's square it. And then let's subtract it again. Remember, we have minus 1 here, then we bring it. Then the next thing we do is that we write our minus 2, and then we pick our squared quantities. When we square this, we'll get a whole expression. So x plus 3 over 4 squared. Remember, this 2 is affecting everything in the parentheses. And this becomes minus 9 over 16 minus 16 over 16. I'm writing minus 1 as minus 16 over 16, which is 1. Now this gives us minus 2 into parentheses x plus 3 over 4 squared. And then minus 9 minus 16 is minus 25 all over 16. When we finish, we are going to expand this over that, so we have minus 2 x plus 3 over 4 squared. Then minus 2 times minus 25 over 16. Minus 2 goes into 16 each times, so this becomes plus 25 over 8. Now when we compare this with our a, x minus h squared plus k, you realize that our k is equal to 25 over 8. Now we know that from minus 2x squared minus 3x plus 2, because this is negative, we know that the curve is going to look like that, something like that. This is a rough sketch, and we know that k is going to be here, which is 25 over 8, and the graph will never go above that. So we are going to say that our range is from negative infinity, that is from here, from negative infinity, from the y negative infinity up until it hits what? 25 over 8. 25 over 8. But because 25 over 8 is part of what we are looking for, less or equal to, we use that. Or we can write this as y is such that y is always less or equal to 25 over 8. And that is the end. I hope to see you sometime next week.